Swayam Prabha. Digital India. Educated India.
Alright, so in the last couple of weeks, we have discussed basically I would say introduction to the polymer physics, and we spent a lot of time on the random walk models of polymer physics, particularly looking at the distribution of the end-to-end distance. So now I want to come to one more quantity that characterizes the size of a polymer chain, which is known as the radius of gyration. Rg. So before I come to this, let us think of the end-to-end distance again and see like what it does not characterize. Of course, it is a measure of, in some senses, the elastic energy is stored in the spring. We got the relation for the elastic energy in terms of Re. So it is a useful quantity, but what it does not characterize. So one thing it does not characterize is the actual length of the polymer chain or its size. For example, I can draw two chains, one of them is very high and the other one is very small, but they still have the same value for the end-to-end distance Re. Okay. Their contour length is very different, but they have the same end-to-end distance. It does not tell you also whether the chain is straight or folded. For example, the chain could also have been like this, like a straight chain, also having the same Re value, right. So although it is a very useful quantity, the Re does not characterize the size of the polymer chain. So if I really think of like looking through a microscope, it will be very difficult to find out where are my ends, and even if we are able to find out where the ends are and we measure the end-to-end distance, it does not tell me much about the space occupied by the polymer chain. Okay. So the quantity we are going to define now, the radius of gyration, tells something directly about the size of a polymer chain in terms of the volume occupied of the polymer chain, and in this sense it is very useful. Okay. So the way it is defined is, if you look at a polymer chain, it of course will occupy certain volume, and let us say if that volume is V, that is the volume occupied by the polymer chain in space. Now if I draw a sphere that has the same volume as the space occupied by the polymer chain, I would call the radius of that sphere to be the radius of gyration. Okay. So I want to point out here that this is not quite precise, in a sense that there can be a prefactor between the radius of gyration and the radius of equivalent sphere, but it gives the idea in the sense that it captures the effect of space occupied by the polymer chain in the system. So you think about it as, I will draw a sphere of a volume V. This will be an equivalent sphere. This is the volume of the polymer chain, this will be something like 4 by 3 pi Rg cube. Okay. So, Rg is defined as the radius of equivalent, it is only equivalent in terms of the volume. Of course, the sphere is by no means a good representation of the polymer chain, it is only equivalent in terms of the volume of same volume as the polymer chain. By the way, the idea of Rg is not unique to polymers. We can also define the Rg values for other kinds of things, let us say rods, discs, cylinders and so on, and we will discuss that towards the end. The way the Rg scales with the number of monomers or repeating units in the chain is something that is unique for the polymers. Okay. So, by definition, the Rg squared is defined as where I may represent the segments or the beads of the polymer chain depending on how are we representing it. So, within a theoretical model we can think of Ri as the position of segment or a bead, and within the experimental situation we can associate, for example, the position of the carbon atom or something that we can see. Okay. So, the idea itself is very general, but it depends on where I am applying this idea. So, for a bead spring model, the Ri would refer to the position of those beads in space, and the center of mass Rcm then is simply the arithmetic mean of those positions and this particular quantity that we defined, we always look at the Rg square value is the radius of gyration. Okay. So, let us now do some arithmetic simplification of this particular quantity. It will be like slightly longer, but then you will realize basically two aspects. One, what kind of mathematical exercise happens in polymer physics, and then we will say also some meaning to the simplified expression that we will derive. Okay. So, let us start with this particular quantity. Of course, I can expand the square, and then what I will get is 1 by m I going from 1 to m Ri square plus Rcm square minus 2 Ri dotted with Rcm, and then what I am going to show is this will be equal to 1 by m square I from 1 to m, j from 1 to m, Ri square plus Ri dot Rj minus 2 Ri dot Rj. So, let us look at like how this happens term by term. Okay. So, we will first look at the first term, then the second, and then the third. Okay. So, the first term that we have written is like a double summation over I and j of Ri square. Of course, the Ri square does not depend on j, so j does not appear in the equation. So, I can simply do this j summation and write this as m Ri squared, and then we will have cancellations of m here, and then I will get 1 by m exactly the term we had earlier. Let us look at the second term. So, now of course, we cannot take the j sum away. Now, of course, R I depends on I and R j depends on j, but what we can write this as is 1 by m square because R I does not depend on j, because R j does not depend on I. So, this will be same as which, by the way, is same as the expression for the center of mass vector that we had written. So, this will be same as RCM square, and now I can also write RCM square as RCM square multiplied by say 1 by m, and then a sum over just a complicated way of writing this to get the expression that we want. So, I can sum 1 m times and divide by m, that is simply 1, and then I can move this thing inside, and what I will have is 1 by m I equal to 1 to m RCM square, which exactly is what we had earlier. Okay. Now, let us look at the final term, which is in this case I will move the Ri there, but keep the Rj where it is because it is inside the j sum, and note that then I will have something like again I can move one of these m inside. If I do like 1 by m of what we have here, we get RCM, that is center of mass vector. So, what we get here is which exactly is what we had earlier. Okay. So, now you can see that what we have got here, this quantity is also in the whole square form. In fact, we can write this quantity as I am sorry, it is not yet in the whole square form, but we will get it in the whole square form. So, let us start with this simplified expression of what we started with, and let us see what kind of further manipulations I can do. So, we started with Rg square is equal to and I want to get this into a whole square form. Okay. So, we will do this by noting that the I and j can be interchanged. If I change I with j, it does not make any difference, because I am doing a summation for both I and j from 1 to m. Okay. So, then I can write this thing into two parts, which will be looking like something like manipulation, but keep in mind that it is simply a arithmetic simplification that we are doing. So, what we are doing here is we divide this by 2, and I will write two sums. This is the first one, and second one will be simply the same thing with I and j interchanged. Okay. So, since these two are the same, and if I divide by the 2, I will get the result that I started with. Okay. But now the advantage is, if I add the inside terms here, we get a perfect square. That is, we can write this as something like this. Now, we can do one more simplification. In this case, we are summing for all values of I and j, but since we are summing, since there is no difference in I and j, what we can see here is the summation will be the same for j values higher than I and j values less than I, just because I and j can be perfectly interchanged. The probability of I being higher than j is the same of I being smaller than j. Okay. So, by this logic, instead of summing from I and j both from 1 to m, I can sum j from I to m, and get this particular relation. Okay. So, just to remind you, like what we started with, what we had in the beginning was so there is an advantage of using the new expression than compared to the older expression. The first one we will see in a moment. In the next lecture, I will do a whole derivation of this, where we can say that the Ri minus Rj square can be thought of in the limit of higher values of m. So, I will get a particular relation that I will use, and we will do that just the same way we did the discrete to continuous transition earlier. The other advantage is in terms of the practicality. So, if I am using the earlier expression, then I have to do the calculation in 2 steps. If I know, for example, the positions of all the segments or beads or monomers as the case may be, then I have to first find the center of mass using the relation and using that I will find the Rg square. Okay. The advantage now is with the new expression is I can start with the Ri values and I can directly get the Rg square value without the need of computing the center of mass. Okay. So, if I am thinking of doing onto a computer, let us say there is a program where I want to find the Rg square value of a polymer conformation at every step, both of these calculations, computation of RCM or the computation of Rg square will involve for loops. So, in the first instance I will use a for loop here, another for loop here. In the second instance I will simply use one for loop. Okay. So, what it essentially means is by some sort of arithmetic simplifications that was appearing to be somewhat weird, we are able to find something that has advantage in terms of computation. It will be much more efficient than compared to a earlier expression. So, now ultimately we are not interested in, again as I was telling you earlier, we are not interested in the Rg square of a single conformation, we are interested in the average Rg square for many conformations. Okay. So, the quantity we are interested in then is this particular quantity, and what I will show you in the next lecture is we can do a discrete to continuous transformation and find a relation between the radius of gyration and end-to-end displacement for an ideal chain, and it turns out to be that both are proportional to each other for the ideal chain. So, but before we go into this, I will end the lecture with one small detail about how the Rg has to be experimentally evaluated or experimentally measured. So, if you think of like the way we look at things in a microscope, it has a simple camera arrangement, we look at things through a lens. One of the best way to think of like how the microscope work is take your smartphone camera and zoom to the maximum zoom you can go to, and just think of a microscope as maybe like 10 times more zoom than what your camera have, or 100 times more zoom. The cameras are getting better over the time. Now, this only works, this whole idea is what is behind what is known as an optical microscope, which can work if I look at things which are more than a micron. In this case, optical microscope can tell you everything about the particular particle I am interested in, not everything but a whole lot of detail about the particle. If the things are less than a micron, as the case may be for a polymer chain, or if I want to look at features which are like sub-micron or less than 1 micron, in that case optical microscope is not enough. In that case, what we make use of is what is known as light scattering. Where the idea is that if we have any object, and let us say in this particular case a polymer chain, and if I throw a light of a certain wavelength through this particular sample, the light will be reflected or deflected, and I will measure the angle of deflection, that is referred as scattering. Now, if I want to look at objects of different sizes, I can play with lights of different wavelengths. When, for example, I am using an X-ray, I can see objects which are much smaller than compared to when I use, for example, a visible light. Okay. So, by varying the nature of the light source, I can look at objects in different size range, and this is one principle that is used in computation of radius of gyration. Okay. So, as we will build further in this week of lectures, we will try to associate the definitions we are developing to experimentally measurable quantities, and that is where the polymer physics that we have derived start becoming useful, because so far it was like toy models, descriptions that were giving us similarly qualitative results, but ultimately we have to verify those findings by experiments, and we are actually building towards it. We will think of like how can we get experimentally quantifiable measures of the size of a polymer chain and its structure, and then how can I compare that to the theoretical results that we are developing. So, I will stop here. Thank you.